Right, so hello everyone. I'm Stuart. I did my PhD with EPOCH in York a few years ago. Then I did a postdoc at Warwick where I did some more EPOCH development, and now I'm with AWE, which still does some EPOCH things sometimes. So I do have a bit of experience with the code, and yeah. So I don't know how. Right, quick show of hands. Who has used EPOCH before? Oh, okay. Okay, that's good. Who has never used it but has installed it on their laptops ahead of time for this workshop? Oh, that's good. Who still needs help installing it currently? Okay, that's good. Thank you, Nigel. Right, okay, well, that's going to make the practical session a bit quicker then, but that's good. And for those of you who haven't come across EPOCH before, EPOCH is a class of simulation tool for modelling plasma physics. And typically, when you're interested in modelling plasmas, you have two avenues you can go down. You have the hydrodynamic way of looking at things, and here you typically have a grid of coordinates, and you make some typical approximations about what the plasma is doing in each grid point in your spatial domain. You might say each cell has a density, has a temperature, it's a Maxwellian distribution. And because you're making a lot of approximations about what the plasma is doing, that lightens the computational load that you have to do to simulate it. So here's a little image which I've readapted from the documentation of a hydrocode called Flash. And the image that they gave had length scales on the order of millimeters. And if you're going to see evolution over those distances, it needs to be run for nanosecond timescales. These are very big, long-term simulations you can do. But because we're making these approximations, then you can't really model all the weird stuff that happens in plasmas. You can relax a lot of those approximations with a kinetic treatment. Here we sort of model the actual individual particle distributions that are actually present in the simulation. You might be solving Maxwell's equations directly. You might be pushing your particles with the Lorentz force. And as a result, you can model these sort of non-equilibrium states better than you could with a fluid code. But that comes with a cost, because we're using fewer approximations about our plasma. We have a lot more computations to do, which typically restricts us to sort of femtosecond, picosecond timescales on micron scale lengths. Here's a little composite image which I took from an EPOCH simulation. The mouse is not showing. And you can see that there is a sort of red laser coming in. You have the blue pre-plasma. And what's interesting about the laser pulse here is you can see that it's in these little bars. What you're actually seeing there is the peaks and troughs of your electromagnetic wave. Thank you. Because, so here's your little laser here. Laser pointer for the laser, and because we're on a sort of micron scale length, we can see the peaks and troughs of the laser pulse, which is interesting. Now, what you would typically want to model with a code like EPOCH is, if you have this kinetic simulation, you can get these non-equilibrium states by typically shooting a laser at something. And there are lots of different targets that people like to shoot lasers at, depending on what they want to achieve. Some people are interested in shooting plasma targets. These are the people who are interested in things like inertial confinement fusion. They want to see where the laser energy goes when they're trying to heat up a fusion capsule through ICF. Or you might want to shoot a solid target. These are very good because they're very dense. By shooting a laser pulse into a dense solid, you can accelerate a lot of particles, and you can create lots of different physics. You can get ion beams coming out of it, you can get radiation emission from it. If that radiation has enough energy, it can decay into positron-electron pairs, get pair production, and you can simulate environments like you'd see around black holes, so it's good for studying lab astrophysics. And if you're really clever, you can tweak the laser-solid interaction to produce radiation pulses on attosecond timescales, which was a recent Nobel Prize. Or you might want to just get as much acceleration into your particles as possible. You might want to shoot a gas target and achieve laser weight field acceleration. Now, usually that's where my application talks would end, but I've actually, from the last high-powered laser conference in Abingdon, there was someone who gave a talk about shooting liquid targets. Very similar density to solids, but the advantage of shooting a liquid is because your target is constantly pouring into your chamber, it's very well suited for modern high repetition rate lasers. So you can get all the benefits of a solid target with the refreshment of liquids. I think it was Focus Energy which was doing that talk. But it's a good one. We have all 4 corners of the phase space covered here. So just to talk about a lot of the physics that happens in these laser matter interactions, we have this little GIF here. And it's typically fed into a few different phases. So I'm showing a solid in this one. And what happens here is the laser will come in and it will heat the surface of the solid into a plasma state, where you have free electrons and ions accelerating in these laser fields. And if that acceleration is strong enough, in the case of the electrons, they can radiate synchrotron radiation. So that's straight away an X-ray source if your intensity is high enough. But the laser also acts to push particles into the target where there's, well, no laser pulse. And here the physics is a bit different, so we also have to worry about the way that high-energy particles interact with cold particles. We're talking collisions, Bremsstrahlung radiation, ionization. And then you still have field effects on the other side, so when these electrons break through, you get a large negative charge being built up at the back, which can drag positive ions out as a source of ion acceleration. So these are really complicated systems with quite a lot of physics going in that we need to capture with our simulation tools. Luckily for us, plasma physics is actually very easy, because when you ignore things like ionization and radiation, there's only 5 equations that you need to model. You have 4 Maxwell's equations. Some describe the rate of change of the electric and magnetic fields. And you also have the Lorentz force law, which is right at the bottom for those who can't see it, which describes how the particles respond to the electric fields. And as the particles move, they create a current. That current gets fed back into Maxwell's equations in this term. So the fields affect the particles, and the particles affect the fields, and we have this nice coupled system which can be described quite elegantly with these 5 equations. Unfortunately for us, plasma physics is actually quite hard, because while the equations that we're solving are quite straightforward, we have a lot of particles that we need to solve them for. If we take, for example, a fully ionized solid block of aluminium, we're looking at ion densities of the order of 10 to the 28 per cubic micron, electron densities about 10 to the 29 if it's fully ionized, which means that in 1 cubic micron of target, which is an absolutely tiny target from an experimentalist point of view, you're still looking at tens of billions of ions and hundreds of billions of electrons, each of which has a field associated with it which affects all the other particles in the simulation. This rapidly spirals out into a problem which we can't solve through brute force approaches, which is where a code like EPOCH comes in. EPOCH is the extendable, particle-in-cell, open source, collaborative. The H is silent. It's a very big code base for simulating problems like this. It has MPI parallelization, which means that different computers can be pointed at different parts of your simulation domain so that the load on any one computer is reduced and the code runs faster as a result. It has 1D, 2D, and 3D versions, has a whole breadth of physics packages, so it has quantum electrodynamics, radiation and pair production, collisions, Bremsstrahlung, ionization, and recombination. And it's all written in Fortran, which is a high-performance language, although it is a bit out of date, so there is a C++ version which is in development as well. And the way that EPOCH works, the way that it gets around this sort of n-body problem that we mentioned before, is it used what we call the particle-in-cell loop. And this is where you take a load of particles and you put them in cells. Here, these are macroparticles. They represent huge numbers of real particles. And we have electric and magnetic fields evaluated at one point in each cell. and we iterate this system using the particle in cell loop. So we start off by updating the magnetic field using a discretized form of the Faraday lens law. That one is. We only do a half step. I'll get more into the step types later. But once we have the magnetic and electric fields at the same point in time, we can update the speeds and positions of the particles using the Lorentz force. And then we do the second time step in the magnetic field, so we've done a full one, which allows us then to do a full step in the electric field using a discretized form of the Ampere-Maxwell's equation. Note the current density, which comes from the particle push that we did earlier. And then once we've done that, we can sample our sort of secondary packages. So each particle is given a sort of optical depth until emission. So we randomly say this particle will travel this far before it emits, and the progress it makes towards that emission depends on the cross-section of the process you're looking at. We'll get into all this later. This is just an overview at this point. And if a particle does emit a secondary particle, we need to recoil that particle to conserve energy and momentum. And we can iterate this loop for as many time steps as we want until we've modeled the events that we're interested in. So, there are a few websites which are going to be very useful in this workshop. Two of them are listed here. One is where you'll find the EPOCH source code, which you'll need to clone onto your machines if you've not done it already. The other one has EPOCH documentation. So this is where you'll find quick start guides. It's where you'll find your user guides, which tell you how the simulations are set up. It has developers guides, which tell you all the equations that it's solving. We have a few instructions here. These are how you would build the code, and they can all be found on the quick start pages of the GitHub URL. These slides and all the examples that we'll be covering in these slides are hosted on a third GitHub page, which aren't actually on these slides, but I have written them on that whiteboard, the chalkboard, and that whiteboard. It's in the same EPOCH PIC repository as the other ones are, but it also has EPOCH Workshop 2026 appended to it. There is a 2025. It is very similar. If you can't find 2026, hopefully you can. I was able to find it before. And with that in mind, what does an EPOCH simulation actually look like? So we write EPOCH simulations using the input deck. It is a single text file which describes how the simulation gets set up. And I appreciate you won't be able to see what's written at the back, but this is the input deck for what I call example 1.1, which is probably the most basic input deck I could write, which still shows off a few interesting things. And the input deck is broken into blocks. So you have a control block, you have a boundaries block, species blocks, output blocks, and these all control different parts of the simulation. So in the control block, this is all about setting up the domain and the runtime behavior. We have nx equals 500, so we have 500 cells between xmin, xmax of 0 to 25. So 25 micron simulation range, 1D code, 500 cells planted. We have n part down here is 50 times nx, so we have enough particles to fill each cell with 50 particles. You'll note that 50 times nx is actually an equation, so the input deck can actually support a certain level of maths parsing, like its own computer code language, a very basic one. And information on what it can actually manage is in the maths parsing link in the input deck, or in the code documentation. We also have boundaries, so we've got our simulation domain, we've given it particles, what's happening at the boundaries. I've set them both to open, so particles can escape, fields can escape, pretty simple boundary conditions. We'll come to the constant block later. We've told it how many particles we want to put in, but we've not told it what particles they are yet. And this is where the species blocks come in. So here I've given it a name, these are the electron species, mass and charge, these are in electron units. Normally the code is in SI units, but this is one particular case where we use special units. So 1 electron mass and -1 electron charge. Frac is 1, so In this case, 100% of the particles we've loaded are going to go into the electron species. And we've told it a little bit about what we want the species to do. We've given it a drift, a momentum drift, and we've given it a density distribution in our 1D grid. And finally, we have the output block, where we tell it we want to dump an output file every femtosecond, and we want it to dump the number density only. This way of filtering might seem a bit overkill for this simple 1D problem, but when we come to large 2D simulations, if you were to dump every particle position and every field value for every time step, you would quickly overwhelm any file system that you've got. So it's really useful to get these chosen specific diagnostics out. We also are able to support functions, so these are like if commands, and we also have comments in the input deck marked by these hash keys. And do not worry, I'm not going to go into this much detail for every input deck that I'm going to show. This is just a nice introduction to input decks. But while I am going overkill, let's talk about the constant block a bit. So this is where you can put in values that you control yourself. There are no keys that are pre-programmed into a constant block. You make the variables yourself. In this case, I find it useful to have a kinetic energy variable for our electrons, which I set to 1 MeV. So if ever I wanted to rerun this simulation with a different electron energy, I just need to change that one number. I don't need to figure out what momentum that corresponds to, because I have these lines underneath, which convert that kinetic energy into a total energy, Ke plus me squared, and I convert that energy into a momentum with this square root term. You can do quite a lot with the maths parser with input decks. And then that electron px I can use in the species block to set the drift momentum.
Stuart, whereabouts are the mass and EV and C constants defined?
That is something else which is also defined in the maths parser. So if you go to the maths parser documentation page, which is here, you'll find a big block of all the constants which EPOCH already knows. That's speed of light, ME, electron volts, which is the same as Q naught, so that's 1.6 times 10 to the minus 19. Lots of stuff like that. All the commands that you can do, like these if statements, are defined there. Square root. There are these. It can get quite complicated, but it's all on that page. So I want to talk a little bit now about these functions that we can do. So we can use these very basic epoch functions to build up quite complex geometries. Let's say that in the example that we're looking at, I want to create an electron bunch which only exists between 10 and 11 microns in our 25 micron simulation domain. Initially, EPOCH's going to believe that the density everywhere is 0 if we don't tell it anything. In this first density line, we say that if x, which is a known variable to EPOCH, it's the x position on the grid, x is greater than 10 microns, the density is 10 to the 28, otherwise it's 0. And we go from this flat density to this little ramp density, which is a step in the right direction, but it's not the density distribution we want. So we can then actually create a second density function to say, right, if x is greater than 11, I want it to be 0. Otherwise, use the value of the electron density, which we've already got up to this point. Electron here is the species name, density is an epoch function. And so it says, right, okay, we go to 11, we go back down to 0, but before that, we have this same ramp up that we had before. The net effect is we get a nice little density bump between 10 and 11 microns, which is what we were going for. Once you have your input deck and once you're happy with it, you can run it using an MPI run command. This is because EPOCH uses a sort of parallelism which is MPI based, and it will be compiled with this in mind, so it will be very useful to run it with MPI run. Here, this number 4 is chosen because the machine we're running on has up to, say, 4 independent CPUs on it, which can run its own parallel thing. If you were running EPOCH on a very large cluster, you could have up to hundreds, thousands of cores that would run on to really get you a simulation speed up. And yes, so basically the simulation I've just described sets up a 1 MeV electron bunch, which has a 1 micron size, and it fires it off. Something that's going to be interesting to keep in mind is, what do you expect a 1 MeV electron bunch with a drift velocity, a drift momentum, to actually do? It helps to have a sort of physical intuition of what you expect the results to be when you're running EPOCH, just to make sure that you're getting something out that looks sensible. Now, I will touch very briefly on reading the data. I'll hand off to Joel in a moment, who will talk more about the visualization techniques. But EPOCH will spit out files in an SDF format, which rather unhelpfully means that if you were to double-click this with a text editor, you'll just get nonsense out, because you're not actually writing to ASCII, you're writing to binary, which might seem like an unnecessary abstraction, but it means that you can pack far more data into a given file size, which again is very useful when you go to large 2D, 3D simulations, because even though you're saying, I only want this piece of data at this point, that can still overwhelm the file system if you're not being careful about it. So SDF just gives us a lot more flexibility with what we can use, at the cost of needing a specialist reader to interpret SDF files. So in the past, I've been a big proponent of MATLAB, but very recently, the Python plotting environment has improved significantly. So I'd say both are viable options. And in fact, I'd more lean towards doing Python for this workshop if you're comfortable with that. And if you were to plot the number density from the first time step that you get from running example 1.1, you'll get exactly what we were expecting. A bump between 10 and 11 microns, which goes to 10 to the 28 per cubic micron. I wonder what that will do over time. Right, and there's a very basic view of how you could do this if you weren't being extra clever and using Joel's plotters. Is for Python, you want to create a Python environment, you want to install SDF X-array, open Python, and then this very basic script will be able to plot that density for you. So it has this open dataset term. I won't go too much into this actually, this is going to be Joel's domain. If you wanted to do this on MATLAB, you would just open MATLAB, make sure that it can see the getDataSDF function, and then you would get it through a command like this. You say, get the data for this SDF file. These are the edges. These are the values. Make the plot. So both are, they have the same functionality. It's just a case of whichever you're happier to use. So I think that's everything I wanted to mention in that little section. I don't know how I've done for time. But I will hand over to Joel now, who will go into a bit more detail on all the crazy things you can plot using the SDF X-array function. So take it away, Joel.
All right. Thank you very much, Stuart, for that introduction. Today we're going to be talking a little bit more about how we actually do all this interactivity in Python. I'm a software developer, so I'm not a physicist by training in the first place, but I'm now doing a PhD in plasma physics here at the University of York. But as one of the side projects I've been working on is this nice package called SDF X-ray. So before we talk about what SDF X-ray is, we've got to really understand a bit of motivation, which kind of bleeds in a little bit to what Stuart's already mentioned, which is EPOCH is ancient. It came out before we had any sort of standardization, which means that we had a completely custom binary file type being used, which, as we now know, is called the self-describing file format. Now, because of this, we need a bunch of different ways to interact with this. Now, there are a bunch of really clever ways we did this. One of them was IDL, which is a very old software for kind of loading the file into the terminal and viewing that, but it's paid and it's closed source, so it's crap. GDL is a newer version of IDL, but the problem is it also uses the same type of interface, which isn't so familiar for developers and physicists these days. We've got MATLAB. Yeah, everyone loves MATLAB, but it's paid and it's closed sourced as well, so boo, rubbish. We've got OpenPMD, which is slowly being adopted a little bit within plasma physics. It's this kind of file form, standardized output format, but it hasn't really been widely adopted, despite being around for about 7 or 8 years, I believe. If someone else knows a bit more about this, please do correct me later. But it's not quite got there. And then finally, we've got SDF Helper, which is the original way you could interface with SDF files using Python, using basic EPOCH. Now, the problem with that is it's completely custom. So all of the plotting routines, how everything works in the hood is a bit finicky, and sometimes when you go to actually build SDF helper, you need to run CMake, which feels a bit confusing and sometimes a bit counterintuitive, a bit rubbish to set up. So, why? So that then leads on to SDF X-Array. Fun animation. Yeah, I spent way too much time figuring out how SVGs work for this. So, yes, another Python package. I know, woo, sensational stuff. All right, please bear with me on this one. So this was initially developed back in 2023, so at the start of my PhD, by Peter Hill, who is a research software engineer here at the University of York, and he has a kind of project set up called Plasma Fair, which the idea is it's writing software using the FAIR principles, which I can't quite remember off the top of my head what they stand for, but the idea is basically making software available for everybody to use, accessible, interactable, and just helpful for everybody, really. So how does this actually work? So under the hood, we use something called SDFC. So SDFC is the underlying C library which builds up the SDF files in the first place. This is how EPOCH actually builds its binaries. And we convert that to X-Array. But wait, what the hell is X-Array, right? That's a big question, because that's also, yes, more computer sciencey stuff. So what is X-Array? I stole this off their website, but I think it's a really good quote, which kind of goes over what it is. So X-Array introduces labels in the form of dimensions, coordinates, and attributes on top of NumPy-like multi-dimensional arrays, which allows for more intuitive, more concise, and less error-prone experience. So yes, basically under the hood, TLDR, you're using NumPy. It's NumPy with a bunch of labels on top, which everyone loves NumPy, so that's marvelous. It's open source, which is great. We all love open source. It follows a very similar data model to something called NetCDF. So NetCDF, for those of you familiar with other PIC-style codes or other simulation codes, NetCDF is one of the more popular file formats currently being used. And X-Array has a way to read in those files and output those files as well. So if you prefer to use something like that, that's quite handy. And one of the really nice features about X-Array is X-Array works really well with the rest of the Python ecosystem. So you can get everything out as NumPy. You can use Dask. So what Dask does is, I'll get a little bit more into that later actually, but you can output as pandas data sets as well if you prefer to deal with those. And it also has a bunch of built-in plotting routines. So it just works directly with matplotlib, and you can do a bunch of stuff with that, which is marvelous. And finally, the last feature that's very helpful is because we're now working with the X-Array package and we're translating our SDF files into it, what's nice about it is we can now output our files in different formats. So for example, we've got ZAR, which is a more recent format that's come out, but what's nice about ZAR is it's a much more compressed format than the regular SDF files, so you can actually output files which are on the order of, well, one order of magnitude lower in size to the regular SDF files, which is quite impressive, really. So if you're working with large data sets on a supercomputer, you can translate them to ZAR files and then download them if you want to do local analysis, which is marvelous. Again, NetCDF works as well. And finally, you can output HDF5, which some of you might be familiar. It's like NetCDF, just another format. So why should I use SDF X-Ray, right? This sounds like a bunch of computational stuff all duct taped together, a bunch of rubbish. So, as I mentioned before, we can easily convert to NumPy or pandas. That's absolutely marvelous. So instead of working with the raw data, we can now do a bunch of interoperable operations like you would do with a regular NumPy array. There's labeling, so we get information about the dimensions, the units, and the name on each of our variables, but also at a global level. So I'll explain more about that later. It'll become very apparent. We also have this really nice feature, which you might remember I mentioned Dask earlier. So what Dask allows us to do is it allows us to load only parts of our SDF files into RAM. Because if you've got a very large SDF file, let's say a couple of gigs in size, or let's make this silly. I've got a 100 gig SDF file for some reason. I'm crazy, I've output all the data. Now the problem with that is obviously trying to load 100 gigabytes worth of an SDF file into RAM is an absolute nightmare. I don't happen to have a HPC, well I do have a HPC, but I don't happen to have 100 gigabytes of RAM just lying around just to load in the damn file, which is ridiculous. So what Dask allows you to do is Dask allows you to load not in the actual data, but pointers to the data. So only when you need access to the actual data does it fully load that data in, which is very, very handy. Finally, we've got plotting. So again, this works with Matplotlib because we're just loading, basically we're just a fancy translator which takes the SDFC converter and puts it to X-ray. We've got a bunch of plotting routines available to us in Matplotlib. So if you're familiar with Matplotlib, literally everything in Matplotlib just works with this, which is marvelous. We can do animations. Ooh, who doesn't love a couple of fun animations right for that presentation? That's always really, really fun. So I think that's quite neat. Not very helpful for posters, though, I must admit, which is a bit tragic. We can also load in our input deck files. So our input deck files are how our simulations are set up in the first place. So as Stuart mentioned earlier, input deck files are how we run our simulations in the first place and set those up. But what's nice is that we can also load them in as well to our SDF X-ray. So when we load in an SDF file, it will also look in the same directory to see, hey, is there an input deck file here? If there is, it will also load that in as well as a set of attributes. So you can then also use that information if you need it to then do other operations. And finally, we've also got unit conversion as well, which is quite handy. So if you want to convert from one set of units to another set of units, you can use a package like Pint, which has a wrapper around X-ray, a bit like SDF X-ray, but it's called Pint X-ray. Ooh, original. But it's very nice, so if you want to do that, there's a bunch of nice open source environment or ecosystem built around this. So, documentation, issues, support, and citations. Now, this is all great and handy, right, but we're not magicians. We have no idea if you're using the package, so please tell us if you're using the package, right? So if you can, please support us by starring the GitHub repository. And if you do publish with the paper, please, publish using using EPOCH and consequently, hopefully, using SDF X-ray, please do cite our Zenodo link. There will be a JOS paper, which is the Journal for Open Source Software, hopefully being written at some point in the foreseeable future. If you're having any problems with it, I can't read your minds from wherever you are in the world, so please, please, put an issue, check first the known issues page to see, hey, does this already exist? Is there a fix around it? If there isn't, now you know why there's no fix around it. If you do have an issue and there's no fix for it yet, please just raise an issue on GitHub and let us know what the issue is with as much detail as humanly possible so we can replicate the problem. And if you can't, because of company policy, because of where you work, just email me. I'm more than happy to take on requests and see what I can do to fix this. If you have any new feature requests as well, you've got some funky idea, please just raise a new issue again, because we'd love to hear what you have to say and what you'd like to have. And finally, we've got a bunch of documentation available on this, because nothing's useful if you can't figure out how it works. So there's a bunch of documentation I've spent way too much time working on. But please go have a look at that. Hopefully use it throughout its practical as well. But if there's anything missing on there, please also do let me know. So, interfacing with SDF X-ray. There are three main ways you can do it. So the first way, which Stuart has alluded to, is using just regular Python via the terminal. So you can load in SDF X-ray, load in the data set that you want, and then you can look at the data set here. So you can see we've got our coordinates here, so we've got our time, we've got our X and Y grids over here and our mids of those grids. We've got our different variables, and we've got the attributes associated with our stuff. So that's one way to do it. The problem with that is it's not very interactable or easy to work with. So what we tend to recommend is using a Jupyter Notebook style approach. So what's nice about that is when you load in the data set here, you can see actually it loads in stuff in a nicer format, but you can click on these buttons on the right to load information about their attributes and also their actual data under the hood. And finally, I found this tool by someone at, where was he? UKEA, who developed a tool called XR2E, which takes X-ray data and outputs it into the terminal. So it gives you a nice terminal user interface. So if you're working on a HPC and you don't have access to do a bunch of extra analysis, or you just want to do a quick health check to see, hey, have I set up the number density right in this simulation? You can just do that, load it in here, and you can also do things such as plot specific variables or just explore what is being output. So, yes, one last thing. This actually falls under a larger thing called Beam, which is the broad epoch analysis modules. So this is a series of other Python packages which I've spent time developing. So on top of SDF X-ray, we've also got EpiDeck. So what EpiDeck does, EpiDeck stands for, so the Epi part is Epoch Python. That's why it's that. So EpiDec loads in our input decks, which is how they get loaded into SDF X-Ray, and it puts them into Python dictionaries. So if you want to then manipulate your data in some way or add new fields in specific areas, you can do that. And which leads on finally to the last package called EpiScan. So what EpiScan allows you to do is it allows you to do parameter scans. So what's nice about that is, let's say you want to run a bunch of simulations over several different parameters. You want to do some of those linearly, some of those in log space. You can do that. And so EpiScan goes ahead and you pass in a Python dictionary with what you want, which parameters you want to change, and then it loads in the files using EpiDec, and then writes the files out as, again, input decks using EpiDec. So you can kind of create a nice pipeline if you want to do a machine learning approach, and then finally do your analysis with SDF X-Ray. Yeah, I do machine learning in case you guys haven't figured that one out yet. So now it's time for everyone's favorite part, which is a cheeky little live demo to see, hey, how badly is this going to fall apart? Very. But let's give that a quick go now, and let's see how badly this falls apart. So I will try and make this big enough that everyone will see. Can you read that at the back? Fabulous. All right. So what I'm going to do first is I'm going to load in my data sets here. And I'm using this fetch dataset function, which under the hood goes ahead and fetches our datasets from a stored Zenodo ID. So you can also download these exact same datasets with the exact same outputs right now if you want to do analysis on this. Then if we load in a single SDF file, you can see here's the information about it. So again, here's our different coordinates, our X and Y grids, and our midpoints. And we can go ahead and we can look at the attributes. So we can see that this is the Y grid, it's got units and meters, it is not point data, and here is the full name. So the reason why we have this full name field is because we want this to also be compatible with the regular SDF helper package. So if you're using the SDF helper package, this is that name you're using in the SDF helper package as well. So you can kind of use this as a way to figure out what this is supposed to be using SDF X-Ray. So this also works with our data as well. So we can look at, for example, our derived number density of the electron species here, and we've got our units now, and we can also look at our data. And we can see here, do you see how it only outputs it tells us how many values there are? That's because it's using Dask under the hood to not actually load in our data, which is nice. And then if we move over here, so this is where I'm loading in an entire data set, and now as a result, you can see we have time as well. So if I open up that there, we can see here all the different outputs that we have from our simulation, which is very cool. Once again, same values there. Oh, also the attributes section exists down here. So this will point you to the first file it opens, along with information about which code you've used. So this will say EPOCH 1, 2, or 3D. Very obvious. It also has a bunch of other information, such as the machine that it's been run on. And then finally down here, here's the actual input deck that was used in the first place. So you can see this is a Python dictionary. So if you just load this into EpiDec, you will be able to then translate this back into a regular input deck. But if you wanted to reference some information from here, so such as your laser setup, you can pull that out to do further calculations. So now, actually, how do we look at variables? So we can look at variables by calling ds, which is what I've named my data set. So when I loaded my data set in back up here, I just assign it to the variable ds. So as a result, I can pull out different fields. So in this case, we've got the derived number density electron. So because we're loading them across all of our different times, we can see we have 21 SDF outputs here. So we get a size of 21 by 100 by 100. So 100, 100 is the size of our X and Y grids. And we can see our coordinates associated with that here. We can also see that it's pulled the data into Dask again here, so we're not actually loading in our data. And finally, we get the attributes associated with that. One thing I've not popped in here, but I want to very quickly show you all, is what's nice about this is when I put my quotes in here, it actually lists out all the existing variables and all the existing coordinates inside of our SDF file. So if you don't know exactly what the name of the thing you're looking for is called, you can do this, and this will then pull up all the different names we wanted to look for, such as the time, which then outputs our array and our attributes. We can also, so it's fine and dandy loading in all our SDF files, but we might also want to look at a specific time slice. So we can do that by calling .icell at the end here, so index select. along with the different coordinate you want to do. So in this case, time. If you want to look at X grid or Y grid, you can also slice across all of your coordinates. So if you want to slice across X grid or Y grid instead, you can do that. You can also use the regular select method if you have a time specifically in mind, and you can use method nearest to try and find the nearest value if it can't find the exact value of time you're looking for, which is very handy. So once again, this just returns the same thing, but in this case, only 100 by 100. There's no 21 in here because we're not pulling in the time anymore, as we selected a specific time. So to get the actual NumPy array out, we just call dot values. So in this case, again, I'm selecting a specific time index. Now we get our values out as a NumPy array, so you can do all your operations you want to do on there. We can also plot our data. So if I call .epoch.plot at the end, you'll see, oh, it just builds a nice little plot right there automatically for us of our number density, which is quite handy. Then we've also got, because I've already said this builds upon matplotlib, what you can do is you can also delay your plt.show into the end here, so you can go ahead and plot several things at once. So for example, I'm plotting my total particle energy for my different species. I tell it I want to output the legend for all those labels, and then finally set a title here. So if I do that, it puts it all together in one plot, which is quite nice over time as well. So this has a lot of nice magical functionality, which is very cool. You can go nuts with this. We can also do things such as rescaling the data, like I mentioned earlier with unit conversion. So if you want to rescale your coordinates, so lots of us work in microns, because obviously EPOCH doesn't work very well if you use bigger than micron scale stuff. So you can go ahead and multiply the data by 1e to the 6, because it's in 1e to the minus 6, obviously. Specify the units as microns, and specify which grids to change. So in this case, X and Y. So if we run this and then plot this, you'll see now our data is scaled as we expect it to be for the dimensions we want. That also works for time as well, or any other coordinate you have up there. Oh, animations time. This one's fun. So it is really easy to do. You just call, so in this case, I'm calling again the derived number density of the electron species across all of the times, and I'm just doing .epoch.animate. And then if you're in a Jupyter notebook, you can call anim.show, which renders the actual video for you. So if I make this a little bit smaller so we can see it for a second, we can see now, ooh, look, it just builds a nice animation for us. We can also call anim.save instead. If you want to save the video, you can specify the FPS in there and other things. We've also got advanced animations. So if, for example, it's fine and dandy plotting one thing as an animation, but for example, in most cases, you might want to also plot things like the laser coming in as well as the number density of the electrons. So I'm going ahead and calculating the flux here. So as you can see, I'm calling the pointing flux in X, Y, and Z, squaring all those terms, square rooting that. So you can see this just works directly on the data under the hood. And then we go ahead and we set its attributes, so we tell it what the new name is of the field, and we give it the units as well that it wants. And you can see we can also specify latex stuff like you would in matplotlib, which is marvelous. Then I'm going ahead and I'm only getting the flux where it's above some threshold value, otherwise the whole thing is going to have flux everywhere. And then finally we build ourselves a color map for it as well. Or sorry, normalization map. So then we can call down here, we can say, okay, again, the number density of the electron species and our new flux masked, and we can pass in specific keyword arguments for them, so we can specify like the alpha, which is how transparent it is. We can specify different color maps and different normalizations as well. So finally, this is the last thing I'm going to show you. You can see it's got both the color bars on the right, which is nice, and we can see the laser coming in as well as how the number density of the electrons vary. So that is almost it. Bear with me. Finally, here's the recommended setup I suggest you all work with for this workshop. If you are familiar with Visual Studio Code, I highly recommend using that along with the Jupyter extension, because that will allow you to do what I've just showed you right now in the live demo. It's nice and easy to work with. But again, you can use any of the ways you want to do it. If you're more familiar with just regular Python scripts, go with that. If you want to try XR2E, please go ahead with that as well. We're happy to accommodate what we can. So, as I'm hoping most of you have managed to do, if you haven't, please let me know and I'll come around and give you a hand. We build ourselves a virtual environment, we activate it, we install our packages. If you're running this in Jupyter Notebooks, you're going to want to include quotes here and then specify Jupyter, which will also add a couple of extra packages which are required. Matplotlib isn't installed by default because you might just want to look at the data. You might not always want to plot the data, so some people just want to do analysis. And then finally, Poach is what we use to fetch our data sets from online if you want to do that as well. And finally, the live demo Jupyter Notebook I've just shown you right now is available underneath the workshop details on the EPOCH Workshop 2026. So let's see, can I click this? Yes. Sadness. If we go to the regular documentation here, we can see we've got the workshop details down here. So there's the live demo. Oh, that's still on the bloody PowerPoint. That's really handy, isn't it? So, yes, here we go. That's better. So if we go to the SDF-X-ray documentation, there is a live demo you can download. If you have access to a Google account, you can also use a Google Colab Notebook, which is just an online version of the Jupyter Notebook if you want to do that instead. And throughout this workshop as well, we have all of the scripts on here. So when we're like having it, so for example, the 1-1-1 drifting bunch that we were talking about earlier, you can download the input deck that we have specified for that. You can also download this script here, which is what we expect you to work with. And then finally, there's an outcome of what the plots are going to look like as well. So we have this for each of them right here, so you can see all of the ones on the right here. Same goes for animations as well. So we have actual animations of what those look like over time. So you can kind of compare your results versus the results on here to see, hey, have I actually managed to get this working right, or have I set something up wrong? So I think that's it from me. Are there any questions? Otherwise, we will get on with the actual installation of everything. Pray this all works as intended. Yeah. Any questions?
Right. Hello, everyone. We had the initial introduction slides before. The remainder of my slides that I have on EPOCH are going to be diving into specific parts of how the code works. It's useful to know as a user. It's very useful to know as a developer. And if a lot of you are doing PhD projects with EPOCH, eventually you're going to have to write a chapter about how EPOCH works. So it's very useful to have seen all this stuff at least once and have something to refer back to make that process a bit easier. So in this little section, I'm going to be looking at the field solvers. We're talking fields, we're talking lasers, we're talking boundaries. So I don't know if you actually ran example 1.1, but at the time I made a point where I said it's really useful to have a physical intuition about what might happen. You'll find that if you actually ran example 1.1 as I gave you, a 1 MeV bunch with some width, it's going to spend the entire simulation just sort of shaking in its spot. But if you were to reduce that density to 10 to the 10, then suddenly you have movement. Your spot will go from... someone's going to need to do some magic to make the thingy work again. Where's my laser pointer? Is it this?
Yep. And then top one.
Wonderful. Right. You'll see that it's gone from its initial spot to a different spot, and that's a bit more what we would expect a particle bunch with a drift velocity to do. So the question is, why does our not dense bunch move while our shorter dense bunch, why does this and not this, or vice versa? And the way that we have to look at this is to think about the field solver that EPOCH is actually doing. So I touched on these a bit before. You have your 4 Maxwell's equations. How is that implemented in actual EPOCH? So you can think of Maxwell's equations as being 2 sets of 2. 2 of them describe the evolution of the electric field and the magnetic field over time. And you can think of the other 2 as initial conditions or boundary conditions for those differential equations. Now, if we want to implement these in code, what we can do is we can use a first order method like this, where you can say the rate of change of a property f with time is about equal to a change in property f divided by a change in time. And if we do that split with the top 2 equations, we can get change in electric field is equal to this expression over a time step delta t. Change in magnetic field is equal to this expression. But we need to know what our differences are. So these curls refer to changes in B over some direction, so dBx by dy and all these sorts of terms like that. How do they come into it? So we are actually using a spatial mesh to solve EPOCH equations on. So let's say we have a cell. We know the magnetic field at cell index I, J, K. Then if we want to find the change in some field over a change in y, then we can look at, well, what about these two neighbours here? What's the difference in the B field in this direction divided by delta, I guess it's delta x, this distance, divided by delta x. And by sort of using these neighbouring terms like this, we can gradually build up our curl expressions, which are required for the Maxwell's equations. In order to do this, we need to know where we're actually evaluating our f points on this grid. Is it evaluated in the centre, and then the gradient is midpoint is here? Or are the field points here and here, in which case the middle of the gradient is at this point? These things matter when you're actually coding this up. And so what EPOCH uses is what we call a Yi-staggered grid. And in order to figure out where all the field points are evaluated, there are a few simple rules you can adopt. If you're looking at an electric field, you start in the middle, and if the mesh has a direction for you to go in, say in a 2D grid, you can go in the x direction, you can go in the y direction. If that exists, then you shift it half a cell in that direction. So EX shifts half a cell in the x direction, EY shifts half a cell in the y direction. There is no z direction in a 2D code, so EZ sits in the middle there. And the magnetic field is basically the opposite. So what you would do for B, what you would do for E, you don't do for B, and vice versa. So BX, you move in every direction except X. BY, you move in every direction except Y. BZ, you move in every direction except Z. So X, Y, that puts the BZ there. And by shifting these cells in this way, we find that actually everything seems to be in the perfect position in order to solve Maxwell's equations. So if we want to, do I have an example here? Yeah, so if you consider the EZ update, that will depend on an x gradient of BY. Well, luckily us, there's now a BY to the left and a BY to the right of EZ. So that gradient midpoint is exactly where we want it to be for our EZ update. And this will be the case for basically all the terms in Maxwell's equation. We can also do this sort of half time step shift with the time integration as well. So here's a nice little diagram I have at the bottom here. The best way to go from B at time step 1 to B at time step 2 is to use the electric field at the midpoint of that step. And then you have what we call a second order scheme, which is a very stable way of doing these simulations. The time step in EPOCH is restricted by the cell size. So you want to pick a cell size, you want to pick a time step such that when you multiply that time step by the speed of light, you don't have anything which is greater than a cell. You don't want light to be able to travel between more than one cell in a time step. So as your cell size decreases, your simulation time step also decreases. And this is the way that you control the time step with EPOCH. And this sort of leapfrogging scheme works. The only place it fails is in this very first B update, where you have to go to the half step of the electric field using the initial step of the magnetic field. And with all that in mind, this helps you understand why we're seeing this weird behavior in example 1.1. Because yes, EPOCH can do the time evolution of the fields. What it doesn't do is solve the initial conditions of those fields. So if I go right back to the start, everything in blue is basically ignored. We will assume that you've set up initial conditions where the curl of B is 0 and the div of B is 0 and the div of E is also 0. That's not the case in our example 1.1 because we've just took a load of electrons in. That is by its very nature not neutral. There are no ions there. But EPOCH will assume that the fields are initially 0. And so what that means for the code's point of view is, right, I have the electrons, there must also be an immobile block of positive ions equal to the electron density at the electron position. Nowhere in the code do we explicitly code that in, but it is implied by the field solver that we're using. And so when we initialize our simulation, our electron bunch wants to move, but there's a very strong positive charge that's pulling it back from EPOCH's point of view. That's why our 10 to the 28 electron number density pulse hasn't moved in that slide. You can work around this. You can manually tell EPOCH what your electric fields are at the beginning of the simulation, but this isn't done by default. So typically, if you're not starting with a quasi-neutral target, you might struggle a bit. So that explains, oh yeah.
So why did the 10 to 10 case move?
Because we haven't changed the bunch energy. So in both cases, we have a 1 MeV electron bunch. That is strong enough to escape a pull from a 10 to the 10 density, but it's not strong enough to escape the pull from a positive 10 to the 28 density. And that's why it has moved in that case.
So Stuart, if you were to plot field in the low density case, would you see the E field grow interstitially between the initial point and where the bunch ends up? Because it's growing due to charge displacement.
Yeah.
Right.
It is growing due to charge displacement, but it's not strong enough to prevent it from escaping in that one example.
Right.
Because there's a difference between a field strength of about 10 to the 18 orders of magnitude. It's not something you would see, but you would see it if you plotted the fields. So we also need to consider what happens at the boundaries now, because you can only look at 2 neighbouring field points if there's something on the other side. Eventually, we're going to hit a simulation boundary, what we call in EPOCH the ghost cells. You have the main simulation cells, which are coloured in one colour, and anything below that with a 0 index, because this is Fortran and we only go down to 1, it's not 0 indexed. Anything with a 0 index is the start of our ghost fields. And there are 2 very basic boundaries which we can do straight away. We can assume reflecting boundaries, and we can assume periodic boundaries. And the only quirk of the implementation is figuring out whether you have a point that's evaluated in the middle of a cell or a point that's evaluated on the edge of a cell. As a quick example, let's look at this little map down here. Imagine we wanted a periodic variable, imagine we wanted a reflecting variable which is cell-centered. In that case, 0 equals 1, 2 is minus 1, 3 is minus 2. If it was staggered, 1 equals minus 1, 0 we don't care about, it reflects itself basically, minus 2 is 2. So the actual implementation depends on where the field is evaluated, but it's pretty straightforward what you would do in that case. And that should be enough to be able to run example 1.2, which is the 2-stream instability. You start off with electrons, so this is phase space, px here, and position here. Start off with a bunch of electrons travelling forwards, a bunch of electrons travelling backwards, and you will see the phase spaces start to intertwine into nice swirly GIFs, which I haven't actually rendered on this slide. But you can do with Joel's SDF X-array package. But that's probably one of the only interesting things you can do with fields that doesn't involve lasers. So how do we actually inject a laser with the framework which I've just told you? We need to figure out a way to set the terms on this boundary such that a laser is injected into the simulation, which can be a little bit tricky. And I'm going to approach this by, well, first of all, let's identify the terms that we need. We need a BZ, we need an EX, and we need a BY. The lucky thing about EX is it doesn't depend on any gradients in X. It doesn't need anything from over here. So the only things we need are the magnetic fields on this boundary, because they're the ones that have the dependence from the ghost cells. So we just need to figure out what these are. So let's consider this term here, the magnetic field in the Y component on the edge. Now I'm going to start by doing something which seems completely unrelated to that. We're going to consider the time gradient of this term, Ez. We can express that for time step n as the difference between a later time, which we don't know, and the current time, divided by our time step delta t. That's the first equation which is important. The second one, we're also going to assume that the time step at n is the average of the time step before and after, again, which we don't have, which we can rearrange into this form. So we can say that our electric field, which we don't have, is equal to 2 times the electric field at time step n and minus the electric field at time step n minus a half. And we can put that into our first expression to get this term for the time gradient of Ez evaluated at time step n. The problem is, remember we're leapfrogging. At no point have we calculated the electric field E at time step n. We only have E at time step n minus a half. So, but we do have the magnetic field evaluated at this time step. And so here is where our assumption comes in. For our plane laser, we're going to assume that the only fields on this boundary are incoming plane waves, in which case we can just swap our Ez, which we don't know, for a By, which we do. And we'll parameterize it with this S term here, so that we can write the time differential of Ez for dt as 1 over delta t times 4 Sn plus 2 By at n and Ez at n minus half. These two terms we know. This term we can set for whatever laser that we have coming in, which is great. The only problem is at no point have I told you what By01 is. So we're going to take this general expression here and break it apart a bit. So while we do know the magnetic field at this time step, we don't have it evaluated at this position. But what we can do instead is we can take an average. We can say that the magnetic field here is equal to the average of this magnetic field and this magnetic field. This is the magnetic field we want. So we've now introduced this to our equation, and when you combine that with the Ampere-Maxwell law, a discretized form, you can obtain this convoluted expression for By on our boundary, where the only assumption is that we have a laser coming in, parameterized by this S term here. And so by doing this, we can inject lasers into our simulation. As a very basic example of what that might look like, here is a 1D plane wave. You'll find this in example 2.2. It is entirely controlled by this laser block, where we've told it which boundary the laser is coming in at, what its intensity is, which we need for the S parameter, and also the wavelength, this is the wavelength of the frequency it needs here. We've given it the wavelength, 1 micron at 10 to the 18 watts per square centimeter. And we also need to tell the boundary that to expect an S term, simple laser boundary. It's basically an open boundary, but you can attach a laser to it. And you can see that if you were to plot the Poynting flux, it will oscillate up and down between 0 and 2 10 to the 18 watts per square centimeter, which has an average of 1 times 10 to the 18 watts per square centimeter, which is what we told it to inject. Because of the particular way that I've plotted this, you're seeing both the peaks and the troughs of the electric field as peaks here. So you should be seeing maybe 2 peaks per wavelength, which is roughly what we're seeing. So 1 wavelength with laser. It works as we expect it. It's just incomplete at the front, so we have this little bit of a numerical artifact here. How much resolution do we need in order to plot this? So remember, what we're doing here is we're plotting a sinusoidal wave. If we don't have enough cells to actually show that sinusoidal shape, our field solver is not going to be able to propagate it correctly. So you need a good few cells per wavelength in order to do this. And as a general rule of thumb, I would say you need about 20 cells per wavelength in order to get it, because when you go to this much worse resolution, 20, that's just 20 cells total, not 20 cells per wavelength. But you can see that no laser has propagated into the simulation, it's just noise. It looks nothing like our nice little oscillation up here. So there is a minimum resolution you'll need for this. You can also have time profiles on your laser. So maybe it starts at 1 intensity, ramps up to a higher one, and then goes back down again. Quite often, when we model these, we'll be interested in doing Gaussian profiles. And EPOCH comes with a Gaussian function. Doesn't use parameters which are necessarily going to be obvious to you if you're coming at this from a laser characterization point of view. But what I have here is a constant block which takes general parameters. So if we want the full width of half maximum time to be 40 microns, then we can propagate this down into our Gauss function, and then you can produce a nice little plot that looks like this. We do have some flexibility in when we start the laser. I've chosen the peak, so 10% the peak of the laser pulse as the cutoff. In reality, there's going to be a long tail of low intensity which hits the target before the main pulse arrives, but you need to cut it off somewhere, and I generally do 10% maximum intensity. Same thing applies to 2D as well. You can have profiles in the spatial direction. So you can say high intensity at y equals 0, drop it down, have a Gaussian in the y direction as well as the time direction. And you get these little pulses pushed into your 2D simulations, which are starting to look a bit more like an actual physical laser pulse. The problem with just injecting Gaussian profiles in time and space is they tend to spread out as the simulation goes on. What if you want a fixed intensity at a particular point in space? Well, there is theory to do that. They call it a Gaussian beam, and it has a very complicated profile, which looks like this. But the good news for you is as long as you set up this beam profile on the boundary, EPOCH's field solver will propagate that into a nice Gaussian beam for you, and you don't really need to do much more thinking than that. And we do provide some example Gaussian beam input decks so that you're able to do this yourself. The only point to make here is that we're assuming that this follows the paraxial approximation, which means that this will work provided that your focal spot is still bigger than your wavelength. And the closer your focal spot comes to your wavelength size, the less this models actual real-life laser propagation, and you'll have to do some fine-tuning to get the focus you want. But here's a nice little example of figure example 2.6 for a 2D Gaussian beam. And you can see that we've made it focus at a distance of 10 microns from the laser edge. These are all in constant blocks. You can change the parameters of your laser, the spatial full width half maximum, peak laser intensity, wavelength, focus point with these terms here, which then get calculated into terms in this constant block, which you don't need to touch, which then gets fed into the laser and the Gaussian profiles and the phase and the lambda in order to produce that nice little focus. And you'll notice as well that I've chosen an example here which doesn't follow the paraxial approximation. I've tried to get a really tight focus for our laser. But in order, I've told it I also want a peak intensity of 10 to the 15, time averaged, which means that I expect to see 2 10 to the 15 in the simulation, and we only go to about 30. And that's because we're not really following the profile that we told it we would follow. If you wanted that focus, then you might just have to tweak your injected intensity a bit until you reach the focus that you want there. And it would be good to do that in a simulation without a target, because as soon as the target comes in, it slows down quite a lot. Field solver is basically free in EPOCH. And in case you're wondering why we were seeing divergence before, if you just do a Gaussian profile, you're effectively simulating it at its focus already, which it will diverge from. So earlier you were just seeing the later half of this point here when I was showing it spread out over time.
Stuart, but in the laser block there, you've got profile equals Gauss. So presumably that's specific to the spatial profile of the beam. Is there an equivalent for the temporal profile?
Yes.
Like how would I get like a high order super Gaussian, for example?
So temporal profile I cover in this one. If you wanted a temporal profile with a Gaussian beam, you could just copy in these T full width half maximum. The WT is the waste that you need to feed into the exponential, so you can just copy that formula as is.
Okay.
And then you stick it into your time profile here. You need to tell it at what points the peak intensity enters the simulation, which is what this parameter is. That's your half width at 10% maximum time, which you calculate using this, which again comes from T full width half maximum. So just by changing this, it will automatically adjust the time the peak enters and the width of it.
I guess what I was asking is the profile and T profile.
Yes.
They are intuited by the depth parser, are they? They're just understood variables.
Gauss is an understood variable, that's in the maths parser.
And what about profile and t-profile? Does it just know that you mean space and time in that case?
Yes. So
okay.
if you... Yeah. Sorry.
Profile isn't just space. Profile can be space and time. T-profile was implemented first, is left in for compatibility reasons in preschool. You could just write profile equals Gauss times Gauss.
Yeah.
Okay.
And
right.
while we're on this as well, I will also see that lambda can also be time dependent as well if you wanted a laser with a chirp, which is something that people ask for sometimes. So quite a few of these. Time is a variable which is understood to epoch in the same way that x and y are. It just saves the function internally, substitutes in the current time, evaluates the function, and then that's what it does. So that's about it with the lasers that I wanted to talk about. There are practical sessions as well. So I know a few of you will have started this already, and to be honest, I didn't expect quite the progress which we saw already when we first arrived, but I would like to propose that if you are happy with the examples, and you've run a few examples that you're interested in, you can have a go at producing work which is relevant to yourself, and then come flag us down and we can provide help with that. And the ultimate goal for this is something we did at the last workshop, was to provide a few pieces of, to produce a few figures with this maybe, and then to have basically a virtual poster session where you stand by laptops. We'll break you into teams maybe based on which table you're currently on or something. And then we'll take it in turns to go around and see what other people have done, just to give you an appreciation of what other people can do with EPOCH, or what difficulties people might have when they come to EPOCH simulations. It worked quite well in San Diego. We'll see if it works here. And in case you're thinking, oh, I came to this just to know a bit about EPOCH, I don't really have a plan of what I want to do with EPOCH, I can give you this little example project which you might want to try implementing. Given you're on your laptops, that will run a laser matter interaction with in 1D EPOCH quite well if you go to solid density. You might be able to get away with a 2D simulation if you're running gas targets, because that's lower density, you don't need quite as much resolution. But you can consider shooting a laser at some plasma and seeing what happens. For lasers, I would recommend wavelengths from 300 nanometers to 1 micron. Intensities, maybe that's a bit high. 10 to the 20 or lower, up to 10 to the 24, which is silly high. You've got pulse lengths. These are typical pulse lengths that are used that would work quite well in a 1D code. You could fire in one laser. You could have a laser on this boundary and a laser on this boundary. Your target can be fully or partially ionized. You can run ionization routines if you're interested to see how the target ionizes with time. You can have a flat density profile, or you can have a little ramp where the density goes up from 0. This is typically a good setup if you're looking at laser solid interactions, because the laser will take time to ramp up to its peak in intensity, and in that time it will start to ionize the front of your target. So that sort of density ramp is to be expected. And then for outputting things, you can look at how the density evolves over time. You can look at how much laser energy is reflected or absorbed by the electrons. You can look at the electron phase space, like I showed you for the two-stream instability, where you look at the distribution of momenta at each point in space. And you can also, if you're feeling extra keen and you want to look ahead to talks I'll give later, consider radiation produced in these interactions, the X-rays from synchrotron radiation or Bremsstrahlung radiation. Look at these over time. There are quite a lot of things you can do, even with a very basic 1D pit code, that I think you would be able to get running in the, how long do I give you? About 5 hours before presenting something. So not a huge amount of time, but maybe enough to get some basic stuff down. And with that, I guess, are there any questions before? Joe?
Yeah, just a quick thing. With the laser focusing stuff, there is also on the, if you go to the EPOCH documentation, you go to the quick start guide, underneath basic examples, there's a whole section on lasers if you want to be able to copy some of the code that's been seen on here as well.
Yeah. And all the worth pointing out as well, all the examples that you've seen will be in the GitHub EPOCH Workshop 2026 if you want to start with one of these lasers and then add some targets in. So with that, I think I'll leave you there. Right, hello again, everyone. I am running only a few minutes behind, but in case anyone is interested in where do you go beyond fields and lasers for the next concept of particle and cell codes, I also have some slides where we talk about the particles, the currents, and the particle pushers that we use in EPOCH. So, let me, I'll kick it off then. And then I think we'll have a brief break after this. Is that going to magically work again? Yes. Yes. Good. Right. So, I'm talking a lot so far about the fields that we have in EPOCH simulations, but fields are only half the concept of the code. You also need to put in a plasma, you need particles. Now, I mentioned before that we don't load one computer particle per real particle. We use what we call macro particles. Here we will distribute them randomly within a cell, defined with some positions and momenta. Okay, my laser pointer has died because of a screen death. Will that work? Can I get it back? Did you get it? Nope. Give me 1 second. No, it's there. It's just I can't move it. I know. I think maybe restart. Right, restart. Oh, off and on again.
Works every time.
Because I yanked the HDMI cable out. Right, exciting continuation. So, we will dump the particles randomly inside the cell. We don't give it any sort of structure within the cells. And we load it we give them enough weight that they can achieve the density we tell it to reach in the code. So, for example, we have a 3D cell, we know its volume, and we give it a number density, so we know the number of particles per volume. So we can determine how many real particles are supposed to be in the cell. We will then scale the weight of the macro particles we load such that the sum of their weights matches the number of real particles in the cell. Basically, this equation here, number density of the electrons times cell volume divided by the number of macro particles we put in the cell is the weight of each of these particles. And the weight represents the number of real particles. That's all very well and good in a 3D cell. How do you get the volume from a 1D or a 2D cell? Well, EPOCH takes a very lazy approach and it decides it's unity. So we will assume 1 meter in every missing direction. Now, that might start to ring some alarm bells, but it's not actually that much of a problem. It's not like we're simulating a plasma which is 1 meter rods and then a few microns in each direction. The absolute number of particles doesn't really come into the EPOCH solver. It relies on things like current densities. So we give it a giant area, but then we divide through by that area, and then the current densities become normal and standardized in 1D, 2D, and 3D. So that's fine. You'll just have to be aware of this when you're looking at the weights in 1D and 2D codes, that they have this artificially high factor associated with them. Because we need to give them something. And as a momentum distribution, if we give it a temperature, we will randomly pick momenta from a Maxwellian distribution about that temperature and give those momenta to our loaded macro particles. We can also provide drifts, like we did in the very first example where we had the drifting bunch. And we can give custom momentum distributions as well. So you can really have a great deal of flexibility over how you load these macro particles. Now, a macro particle isn't just in one point in space. They have these shapes. They have they refer to distributions of particles over large volumes. By default, we give everything this sort of triangular shape. So if our particle is given this position here, we will assume that it has a distribution which goes into neighboring cells on either side as well, given a shape function which has this general form here. So if we want to know how much weight is in each cell, which we'll need to know for things like the current motion, then we basically just find the area of this shape underneath each, that falls into each of these cells here, which has a fraction somewhat of this form. But using a fraction of this form, we get the weights in the cells based on this. And as a quick sanity check, we can say, well, what if our cell was exactly on the boundary between two cells? We'd expect a 50-50 split in each. You substitute that condition into our formulas, that is exactly what you get out. You get fraction of a half, Wj and Wj minus 1, if it was, say, here, is a half and half in each cell. Perfect. And if we wanted to figure out what the values of a field were on that particle, then we find the weightings in each cell, and we multiply it by the fields in each cell to find the total field evaluated over the particle position. So that's how we get the fields onto the particles for the Lorentz force push. That's not the only shape that's available to you. If you wanted to have something that ran quickly, where you don't need to interrogate lots of neighbouring cells, then you might be interested in the top hat function, which is a very up and down, one cell wide distribution. The problem with that is it will give you a lot of simulation noise because it's a lot less smooth. If you want to absolutely minimize all your noise and get really smooth distributions at the cost of sampling lots of cells when you do a particle push, then you can use this complicated B-spline function, which is great for solid density simulations, but might be a bit overkill otherwise. So these are the shapes that we can support. That was in 1D. If you wanted to extend it to 2D and 3D, then you take those 1D shape functions and you multiply them in each dimension. So you can build these sorts of pyramid shapes in a 2D, and you can see how that weight is distributed onto a 2D grid below there with this little interpolation factor number. Nice little graphic there to consider. And you can actually see these particle shape effects if you deal with simulations where you have a small number of cells to consider. So if we look at example 3.1, you'll be able to see the effect of particle shapes in your simulation. I've given it a density which says if x is greater than 2 and it's less than 6, then it's 100. I expect the density to follow this square shape. And when you look at the particle positions, they do fall in that square shape. But if you look at the density, which takes the particles and it follows it through the particle shape, you can see that it's losing some effective density outside this window because of this particle shape leakage. So this is something you can see. I would say, though, that most of the time you're not going to be looking at geometries which are on the same size as your particle cells. So you're unlikely to actually ever see this in practice. But it is something that you'll see if you have like 8 cells and your density is sensitive to specific cell numbers. So, now that we can load our particles, how do we push them? We will take the Lorentz force. The rate of change of momentum is equal to Q times the electric field plus particle velocity times B. We can rewrite that into a relativistic form, so we use relativistic momentum for the... Oh, that should be a P, that's not... Anyway, that's fine. That's what it should look like in discretized form. Oh no, it is a V, never mind. And we're doing P divided by gamma m, which is how we get around that. So that's the relativistic form of the Lorentz force. And we want to be using our magnetic fields and electric fields evaluated halfway through our step for second order accuracy. This is why, by the way, at the very start, I was saying that we do our B push in 2 steps, so that we briefly have an estimate for the magnetic field at the half step point, which is evaluated at the same point in time as our electric field, before we complete the full magnetic field jump for second order accuracy in the field solver. So once we have our fields at the midpoint, we can just push our momentum across using these time-centered values, looking something like this. There are some unfortunate quirks with this equation, though. You'll see we need the momentum at the midpoint when we only really start with it at the start of the time step, and the gamma factor at the midpoint as well, which we're going to need to work around here. So we can use a similar trick to what we did with the field solver and replace the momentum at the half-time step with the average of the momentum on either side. But now we have a bit of a gnarly equation to solve because we want Pn plus 1. It also appears on this side of the equation as well. That's going to be something that's quite complicated. And so what we can do instead is we can take a bit more of a different approach. So instead of going straight from Pn to Pn plus 1, we'll go via these intermediate P minus and P half variables, which have half the acceleration applied, which should, in principle, give us a gamma factor for halfway through the step as well. And when you substitute these expressions for P minus and P plus into the above, you can get this term which links P plus and P minus. Unfortunately, we've not actually solved anything because, again, we have P plus on both sides of this equation. So we're going to have to get a bit more complicated to find this missing link between P minus and P plus. And we can do a Boris algorithm, we call the Boris pusher. And in doing this, it relies a lot on geometry, and it relies a bit on some of the algebra as well. We will define two new vectors, one which points in the magnetic field direction, or opposite depending on the charge, and we'll invent this new P prime vector, which is the P minus plus P minus cross that new vector that we've created here. It will look something like this as your P prime. And the useful thing about P prime is if we were to now take the cross product of P prime and T theta, then we can actually get a vector which points from P minus to P plus, our P plus minus P minus vector. And if you go through all the algebra, which I'm not going to do, you can find that with this scale factor, you can actually produce an expression which links P plus directly to P minus, producing the missing link here and allowing you to jump from Pn to Pn plus 1. So we call the Boris algorithm.
Stuart, is there any way of doing this implicitly?
You could do it implicitly. The Boris pusher is quite a quick process, and it usually has enough accuracy for the problems that we're interested in. Quite often, in these hardcore pick conferences that you can sometimes go to, there'll be a whole list of reasons why the Boris algorithm is rubbish. But for the most, it's usually about highly relativistic cases, I think. But for the vast majority of cases, it's usually fine. So I would recommend sticking with it. I think EPOCH provides a Vey pusher as well, which is slightly different, but I've never found a need to use it. And the last thing to touch on then is going to be the currents. So we'll start with the continuity equation. The rate of change of current density, of charge density, is equal to minus the divergence of J. We can do our usual trick of breaking this down into a change in charge density divided by change in T is change in the current divided by change in X. And this allows us to rewrite this of the form, in this case, J2 minus J1, our X gradient, is equal to delta X divided by delta T minus this term here, which is the change in the charge density. This is for this particular example here, where we start with this dashed weight distribution, which has weights and cells of these values, and then we go to a second weight distribution, which has weights and cells of these values. Cell 2 has a change of 0.3, which is where this 0.3 is coming from here, times the weight, times the particle charge, divided by the cell volume. We can solve this equation because we know from the construction of the particle shape that in the leftmost edge, there is no charge passing that plane. So J1 must be 0, and this expression gives us our J2. And now when we're looking at the change in weights here, we know the current on this boundary, so we can deduce the current on this boundary as J3 is equal to the old one, plus the weight change in that cell, And we can just keep iterating along the particle shape until we've evaluated the current on each of these cell edges. That is if you have a current which is in the grid direction, but remember we can have reduced dimension codes. You can have EPOCH 1D where you don't have a grid in the Y direction, or EPOCH 2D which doesn't have a grid in the Z direction. So we can't actually track the weight change over the grid. We have to use something else. So we will just simply use current density is equal to charge times speed. This is the charge of a macroparticle in a given cell. And this G is the average value of the weight in that cell during the full time step. As an example, I give here cell 2. Cell 2 starts with a weight of 0.4, it ends with a weight of 0.1. That means on average it has a weight of 0.25 in the cell, has a charge of the electron charge, has a weight of, sorry, this is a factor applied to the weight, it's not the actual number of real particles. So we take the actual number of real particles times the charge of each one to get the total charge, divided by the cell volume, multiplied by the speed in the emitted direction, multiplied by the average current, the average weight fraction in that cell. And that's how we get our emitted direction currents. The only complicated part is when we do JZ in an EPOCH 2D code, because we need to average that weight fraction with simultaneous movement in the X and the Y directions, which produces an equation which looks like that for your average weight in the cell.
Stuart, ask one brief, dumb question.
Yes.
So you've talked a lot about how the code has to handle different dimensionalities differently. Am I being stupid, or is there? You've not mentioned axisymmetry, so that you can do 3D simulations assuming azimuthal symmetry around, so that it's really a 2D sim, and you're just saying that it exists the same all the way around a reflection axis.
There is a cylindrical version of EPOCH. It is going to be touched on tomorrow. Okay. It will follow generally different rules from this, and because it's a bit of a niche case, we're not really going to talk about it in that much detail.
So forgive me if this is like a total new question, but I think in some PIC codes they have a kind of thing where like you can create and destroy new macro particles, and like the number of particles in each macro particle can maybe change, or is it in this case is it that the number of the macro particles themselves have a constant number of particles in, and those macro particles are sort of like conserved, and you don't create and destroy them? Or
are you talking about particle splitting, what they would call? So you take one macro particle of weight W and create two macro particles of weight W by 2.
Yeah, exactly. And then as a way of sort of like being able to sort of I guess like track something else which you might be interested in, or which the code might automatically decide needs to happen.
So there is some sort of weird reweighting behavior that can be done with certain physics packages. Like when you emit a photon, you don't have to wait for the full macroparticle weight to emit that photon. You can say, we'll boost the rate artificially, but we'll decrease the weight of the produced photons to conserve real particle number. Mm-hmm. I guess it's a bit like what you're saying.
Yeah.
But generally, for the core PIC algorithm, the weights are decided at initialization time, and you do that to meet whatever density that you're trying to do with however many particles you've got, and those weights remain fixed throughout the simulation.
Okay.
Unless some weird physics package is changing them.
Yeah, I think I'm thinking about like a alpha particle type stuff.
Yeah, I can imagine that would be a place where that particle splitting would be appropriate, and that is something that can be done. That would happen separately from the current solve.
Okay.
So when you're calculating an average weight of a particle in a given cell to do this, then you wouldn't consider, well, halfway through my step, it is split into two particles.
Sure. That's
a later thing.
I was thinking more generally, but yeah.
Yeah.
Right.
It's something that can be done, and it's something that EPOCH does at times, but generally, for the core Pilk algorithm, the weights don't change. And the last thing I want to touch on here is, well, actually, it's not the last thing. The thing I want to touch on halfway through is self-heating. So earlier I said that there is a limitation on the cell resolution that you need in order to have laser propagation, and that is true. But usually, the more stringent resolution demand comes from your particle loading. Because if you think about it, when you go back to this cell example here, if you had a real physical number of particles per cell, forget macroparticles, forget weighting, I stick 10 to the 10 particles in a cell, then the current distribution is going to be quite smooth if it's completely noisy. If you have 10 to the 10 particles plus 5 passing one boundary and 10 to the 10 particles passing the other, the actual difference in currents on either of those boundaries is going to be incredibly small. So the currents themselves, the net currents, are going to be quite smooth. When we switch to macroparticles, suddenly our macroparticles have loads of weight. So as soon as they pass a boundary, that's going to cause a really high current spike, even if we spread it with these particle shapes. Current spikes will produce spikes in the electric field when it gets fed into Maxwell's equations. And because Maxwell's equations are sensitive to spatial gradients, that large non-physical ramp is going to propagate into the B fields, which comes back into the E fields, and we'll get artificially high fields, which will accelerate particles artificially. This is a problem that all particle and cell codes will have, and it's not something that you'll ever be able to truly get rid of. What you can do is minimize these problems by picking a resolution which is great enough that your particle movements don't cause as high current spikes. So what we would recommend is whenever you load a target to simulate a small region of that target with periodic boundaries over a long period of time. In this case, I'm doing a 10 by 10 cell simulation for 300 femtoseconds, and I'm giving it a certain cell size and a certain number of particles per cell. By doing periodic boundaries, that plasma then is uniform over all space, and you would expect physically, you would expect no increase in temperature over time. So any increase that you do see must be due to this artificial self-heating. So I have a few examples here. If you do a target with, and I think this was for an electron density of 10 to the 28 per cubic micron, per cubic meter. And if you do a cell size of 50 nanometers and 10 particles per cell, your temperature increases by 50% over the runtime. This isn't ideal.
Is that assuming triangular shapes?
This is for triangle shape, this one. The default is triangular shape. The self-heating gets better as we move to smaller cells. So at 20 nanometer cells, the heating is dropped. At 10 nanometer cells, it's dropped significantly. And why is this? Well, if you have a smaller cell with the same number of particles per cell, your cell volume is smaller. And if your density is fixed, then you need fewer real particles to fill that cell. The weights of the macroparticles are coming down, which means they cause less of a current spike when they move across a boundary. You will get the same thing if you keep your cell size the same and just increase the number of macroparticles. Suddenly you can reduce the weights because there's more of them to build up to that density. And when we keep 50 nanometer and go to 100 particles per cell, again, you see a much better heating profile than you do with these runaway ones up here. Two final tricks which you can use are current smoothing. So the control block has this smooth currents variable which you can set to true. Very useful for solid density simulations. What it does is it takes the current in one cell and averages it by the currents of the neighboring cells each time step. That is a really good way. That's the dotted line. So that's the bad resolution, but with current smoothing, it does much better than without. And by far and away, the winner in this example is switching to a bigger particle shape, going from triangular shapes to B-spline shapes. Sorry, that's it.
How come they are the default if they work so well?
Because it's slower. When you have a B-spline, you have 5 cells in each direction. In a 2D code, that's 25 cells you need to interpolate to your particle instead of just 9 for the case of your triangle. So moving to smaller cells, bigger time step, longer simulations, more particles per cell, more particles to push, bigger simulations, current smoothing, an extra step, bigger simulations, B-spline, more cells to interrogate, bigger simulations. All of these come with a cost of runtime. It is the job of the particle in cell coder to balance computational expense with reasonable performance. In this particular case, we have heat. We see even in our best case scenarios, the heating does rise by a few percent. But suppose we're interested in hot electron generation, where the hot electrons have energy on the order of a few MeV, 10 MeV. Do we care if our background plasma has risen in temperature from 1 keV to 1.1 keV if the only diagnostic we're interested in is the 10 MeV electrons? That is another thing to consider. How much self-heating you can get away with will depend on what you're actually interested in modelling. If you want to do bulk laser heating as a function of time, then yeah, maybe looking at the bulk temperature and keeping that self-heating down is an appropriate way to go. So, see a question?
Is it what's the kind of how linear is it with regards to the number of particles per cell and the cell size? Would it be preferential to increase the resolution or increase the number of particles?
I think so. I don't know the functional form, but I do know you get better benefits for going to smaller cells and keeping particles per cell fixed. That is also more expensive, though, because not only are you increasing the number of cells to model your simulation window, you have to then load more particles into those more cells, and because the cell's smaller, the time step of the simulation is also smaller, so you need more particles and more steps with that. If you want to play around with the effects of self-heating, example 3.2 has this very basic self-heating deck. You can plug in your own densities and temperatures of interest and see what, under simulation runtimes as well, and see what effects these have on what you're doing. And one of the last things, I think it might actually be the last thing I want to talk about on particles, is when you're running diagnostics, you can sometimes get out particle spectra. You might be interested in the distribution of electron energies, say. Now, this is a concept which has confused people in the past. If you get it, it's really straightforward. But the first time you see it, it's going to look really weird. So, if I wanted to show off a spectrum, I might just say, here are my energy bins. I'll just count the number of particles in each bin, and that's going to be easy. You can do this using a few different tools in MATLAB and Python, and you will. The problem is that these diagnostics are dependent on your bin size, and if you were to use, say, 6 bins, my spectrum peaks at 25. If I use 12 bins, my spectrum peaks at 14. It's not very useful for comparing one data set to another data set if you're not really comparing the same thing each time. And the bin size is arbitrary. We don't want our results to depend on the number of bins that we're using. So what we can do instead is look at differential spectra. If we take those same bins, but divide them by the bin size, then we produce plots which are a bit more similar in terms of peak, depending on whether we use 6 bins or we use 12 bins. It's the same data each time, and the physical and the reason I call them differential spectra is that the physical interpretation of this is if I wanted to know how many electrons have energy between 9 and 13, then I would calculate that by taking the integral of this curve between 9 and 13. So that's why it's dm by dE, because when you integrate over dE, you get a number out. It's a very useful way of doing it, and it's what the plotters that Joe has come up with actually do. So at the end of these slides, we have a few different examples of how you might load a complicated target. This is the same sort of logic as we had in the very first example of the day. We can build up big targets in 2D with a sequence of if statements like this. So in this case, our basic target, if x is greater than 15 microns, it's this density, otherwise it's 0. If x is greater than 20, drop it to 0, otherwise the same. We've built up a block in 2D space. We can look at the distribution of particles' kinetic energy. You can see that it follows a Maxwellian distribution here, at least I hope that's a Maxwellian. And this is a sort of differential, this is an example of a differential spectra. So the integral between two limits tells you how many particles have been loaded with energy between those two limits. Very useful diagnostic. You can load different momentum distributions. Here are some examples. This is a standard, so we're looking at the px, the momentum in the x direction now. Normal temperature is the blue one, which is just 10 PV. 10 PV with a drift is the same distribution but shifted. We can even give a custom momentum distribution. So we'll say the momentum distribution will be in the range of 0 to 10 to the minus 22, and we'll have this function px divided by 10 to the minus 22. And what it will do is it will randomly sample a px in that range, substitute it into this function, and then use what we call rejection sampling to determine whether or not it keeps it. So we have a function which is proportional to px. That is the end result of what our momentum distribution looks like. And you can ask me more about that if you're interested in custom momentum distributions later. Most of the time, a simple Maxwellian is probably going to be good enough for what you want to model. And we also have some funky targets. So we can also go really crazy with this constant block and produce rotated coordinate systems, which we can define our density in. So if x in my rotated coordinate system is greater than 0, set it to this, otherwise 0, and you get these nice little rotated targets. I can produce repeating functions using this floor function. So take a fraction, subtract its floor, I get something that repeats, and I can use that to create a repeating circle target on the front. Now, there's a lot you can do with the EPOCH input deck in terms of custom targets. And now, that's about it, I think, for the... so lastly, I'll say that because we're only simulating the peak laser intensity hitting the target, we are neglecting the long intensity rise up to that peak that will be already hitting the target before our main laser arrives. It'll be ionizing that target. Typically, at least in a laser solid simulation, you'll be shooting a preformed plasma with your main pulse, what we call the pre-plasma. So you can add a exponentially decaying plasma to the front of your target to better model this physical reality. And you can model the pre-plasma with different codes. You can try a range of different pre-plasmas to see how pre-plasma behavior affects absorption. These are all things that you can look into. And to be sure, because as you're probably aware of by now, there's a lot of hand-wavy stuff going on here in terms of, oh, the self-heating is probably fine. The pre-plasma is probably fine. What you can do is you can try convergence testing your final result. You can run your simulation, one set of diagnostics, one set of simulation setups, and then try increasing the resolution. And if your simulation outputs don't change, you probably have a resolution which is acceptable. I think the final point says it all. Physical results do not depend on numerical parameters like cell size. So that should hopefully be enough information now to create simulations where lasers come in and hit targets. I don't know if anyone else has questions on that, or if you're happy to have a coffee break, I think, as we're approaching.
Mm-hmm. Yeah. Just a quick thing to add on. It's completely irrelevant of what Stuart just talked about, actually, but if you're using VS Code to have a look at the input deck files, there's an extension you can download called Deck Language Support, which gives nice syntax highlighting when looking at input decks, which just makes them slightly easy to read. That's all I wanted to say.
Oh yeah, I forgot about that. That's a good one.
Yeah, I should have included it in the slides. Yeah, cool. Otherwise, yeah, coffee break now, and then some project work until about 1:45.
Yes, I'll be doing my last talk of the day.
Yeah.
Right, I think I'll take a moment then to just have my last talking session of the day. we've covered everything that you need for the standard particle in cell loop, the currents, fields, the boundaries. But EPOCH has some additional physics packages, some extra things that it can do beyond the standard particle in cell loop to produce some interesting results. So let's talk about these briefly. This is, I believe, a list of all the physics packages which EPOCH is capable of simulating. So you can break these down into different categories of package. If we have a particle interacting with some sort of background species without changing the species, like Bremsstrahlung radiation, where an electron zips in and it radiates photons in the presence of other ions, but it doesn't really do anything with those ions, then those are your background species collisions. Sometimes it can interact with the background fields. So field ionization, you have ions ionize in the presence of a strong field, but with no other particles needed to do this. And then you have your more complicated processes where you have a background species and an incident species, and both interact with each other to change them both. So you can think about this in terms of collisions. Two particles come together, both of them are affected. Now, this made me laugh a bit. Because of where I come from today, I can only present these slides if I make it very clear that the nuclear trident pair production and QED trident pair production refer to physics packages and are completely unrelated to anything my company might do. Right, point made. Okay, so, yes.
With the recombination packages require an atomic model as well, and does that also?
I might touch on the recombination stuff later, but just in case I don't, it is based on recombination rates taken from FlyCheck, and the 3-body recombination is done using detailed balance models with collision ionization.
Sure, yeah.
So that's how they work. The generic EPOCH physics package can be described as having you have to sample when a package triggers. Usually we'll wait a certain amount of time, or the conditions will change, and then something will happen. When does the physics happen is what we're trying to figure out. We can imagine that if we have a rate of an event happening of lambda, then let us define the probability of an event happening over a time delta t is equal to lambda delta t. That's the jumping off point, which means that the probability of no event happening over a longer time period, big delta t, is equal to the probability of it not happening in a small time period, n times, where n small dt's is a delta t, which comes out to this expression here. As our time of interest goes smaller and smaller and smaller and smaller, this expression tends towards an exponential, which means that the probability of at least one event happening over a long time period is equal to 1 minus exponent minus the rate of that event happening multiplied by delta t. And that is our key equation that basically all the physics packages use in the background, but just in different ways. So let's consider what we call the optical depth of emission method. We will replace this lambda delta t term with this property we'll call tau. That's the optical depth. And that is the time integral from 0 to delta t of the process rate lambda. Because the rate can change as the particle moves along. Let's say you're Bremsstrahlung and you need to be colliding with background particles. When an electron is in a background medium, there's a high rate. When it's in a vacuum, there's no rate. So we need to do the time integral of that rate to figure out how far through our emission process we are. We can convert it into a probability density function, and we can invert it to what we call a cumulative, I think that's a cumulative density function is what that stands for. And basically, by rearranging this, we can say that the optical depth of emission is equal to the natural logarithm of minus xr, where xr is a uniform random number. So for every particle, for every process, we will calculate ln minus xr, we'll sample a different xr for it, and that will be our optical depth to emission. Now, when every particle moves, we will calculate this integral to figure out its optical depth movement, and when it hits the optical depth of emission, then the process will trigger whatever that process is. And if the particle survives the process, we will give it a new optical depth for the next emission. Now, a lot of the physics packages then will require us to track these optical depths for it, which means we have an extra particle variable, which means we have more memory associated with each particle. This isn't great when you're talking about what you can run on a single computer and parallelism. We don't want to have blank arrays for processes we never use. So what we do instead is we lock a lot of the physics behind these compilation flags. You remember when you first compiled EPOCH at the start, you were running make compiler equals gfortran something. Well, there is also a make file associated with each one, and in that make file you'll find a section like this with a lot of defines commands which are commented out. If you want to use one of these physics packages, so for example, photons is QED emissions. There's also where we hide the different particle shapes if you want to run with different particle shapes. Bremsstrahlung radiation's there as well. If you uncomment that defines, then run a make clean to get rid of your installation, and recompile with make compiler equals gfortran again, then you will have access to the extra compilation flags needed to run these physics packages. Particle shapes, physics packages, extended I/O as well. Sometimes if you want to know the time particles pass probes, or if you want to give each particle a unique ID value, these are also hidden behind compilation flags. Now I'm just going to go very briefly over all the physics packages I could be bothered to write up. We have two types of radiation. So two processes will emit photons in EPOCH. You have Bremsstrahlung radiation, which is defined by the Seltzer-Berger tables. It has cross-sections as a function of incident electron energy, which look like this for different materials. Then you have nonlinear Compton scatter, which is radiation due to acceleration in laser fields, which scales with this chi parameter, which has a rate which is different for different field strengths, I think, and different electron energies. Have I written field strength anywhere? It must have field strength.
Chi's depending on field strength and energies combined.
That's it, yeah. So we have a trigger rate. So in Bremsstrahlung, the trigger rate is the ion number density multiplied by the cross-section and the particle speed. For nonlinear Compton scatter, the trigger rate is a lot more complicated. When a photon is emitted by this code, we don't just plug that into the EPOCH field solver, because that tracks photons with wavelengths of a few microns, whereas these X-rays will have wavelengths of nanometers, 10 to the minus 10, really small wavelengths. You can't create a grid which can track those, so instead we treat them as different particles. If an incident electron emits a photon, that macro photon has the same weight of the incident electron, and the incident electron is recoiled to conserve energy. We have a differential cross-section for the case of Bremsstrahlung, maybe, where we have this sort of PDF as, for a 1 GeV electron and an aluminium target, the probability density function for emission of electron energy looks like that, which we can invert into a cumulative density function, pick a random number between 0 and 1, read it across, read it down. That's the energy that we're going to inject for that electron. Very basic sampling, as long as you already know this complicated probability density function. Pair production follows a very similar rule. So we have a few different pair production mechanisms. We have Bright-Wheeler, where a photon decays in the field of an intense laser. We have QED Trident, where an electron radiates an electron-positron pair directly. And we have Bethe-Heitler pair production, where a photon decays in the electric field of a target nucleus. You can think of these as the equivalents of synchrotron radiation and Bremsstrahlung radiation for photon decay. When we have a pair production, we destroy the photon if it's a photon decaying into an electron-positron pair, or in the case of trident pair production, we will simply recoil the electron to conserve energy as the two new particles are created. And again, we have a cross-section as a function of energy, and we have a differential cross-section which tells us the particular energies that the pair particles might have once they're created. Yes?
Yeah, possibly dumb question again, but so when you're talking about photons, these are macro photons in the same sense, so they're not to do with the EM field.
No.
Right, so the classical EM field that's actually representing the laser, right, this is almost like post-processing.
Yes.
In a sense, right, okay.
It's post-processing, but
intelligently feed back through recoil.
Yes.
Right.
Now, a standard photon will not impact anything that's going on in the epoch pick loop. It's invisible to the field solver, it's invisible to the particles. The only way that these macro photons do anything is if they later do a pair production into an electron-positron pair. Suddenly we have charged particles again, the field solver can see it again, so it is important to track these macro photons just in case they do something like that. If you're not interested in those macro photons doing anything, you can switch off their motion and it won't affect the simulation, because if they're not going to decay into something else, then their tracking their movement is irrelevant. And actually, it can speed up the simulation quite a lot if you don't track photon movement, if you don't need to.
And how many photons is a macro photon representing? Is that because you said at the beginning that your density and volume is essentially determining the weight associated with the macro particle?
Yes.
Like how many physical particles that represents. How do you make the decision to say how many physical photons does this macro photon represent?
By default, the macro photon has the same weight as the macro electron. But that can produce quite rare events, because if you have a macro electron which has, I don't know, 10 to the whatever number of electrons in it, the probability of all those then producing a photon is going to be quite low, because the chances of there being 10 to the 10 photons in your simulation might be quite low. What we offer instead is a way to scale down that, so you can say, right, I'm going to artificially increase the cross-section, but I will decrease the weight of my emitted photons in order to conserve real photon number and to get better statistics. Now, there are issues in a particle recoiling a particle of a different weight. I think that in EPOCH at the moment, we don't really have much of a fix for that. We have a very basic model where we just conserve energy and we just recoil the electron as if it's emitted half as many photons, say. But there are other ways you can do it, and I think that might be an area that's actively being worked on at the moment. So here's a little example of what you could do. Example 4.1 models Bremsstrahlung radiation. We will start with an electron bunch in one cell, and we will let it propagate through a background medium of ions, and we will track the macro photons that are created over that simulation. In order to do this, we interface via this Bremsstrahlung block. It is listed in the EPOCH documentation. Switch Bremsstrahlung on, have it run for all times. Yes, make photons, but photon dynamics is F. Don't move them. We don't care about moving these photons. Let them just sit where they're created. And yeah, that's basically all the properties that we're setting here. And this produces a Bremsstrahlung photon spectrum, which looks like that. Very good way of looking at the radiation that you produce when electrons move through materials. Bright wheeler pair production, we can set up a test for this by shooting a bunch of photons at a laser pulse. So this is our photon beam species. We give it some drift equivalent to a 100 MeV photon bunch, hitting a laser of 2 × 10 to the 23 watts per square centimetre. And we can look at some of the electrons and positrons that they create, looking at the number density. What I think is interesting here is that it sort of follows the ups and downs of the intensity of the laser wavelength a bit. Probably not exactly, Sorry. Actually, I think, yeah, it does look quite similar. I can believe there are 10 wavelengths there.
I think they actually use the shrouds. Stuff I'm looking at them, which is interesting.
Oh, cool. Yeah, so there's a... Yes. So that's bright wheeler pair production. That's example 4.2. So we can also have ionization and recombination processes as well. Now, EPOCH understands species based on giving it an atomic number to know how many electrons it could have, and a charge to know what charge state that ion currently is. And then we can calculate ionization and recombination rates from that data. If an ionization occurs, we can move our macro ion from one species to a species with a different charge state, and we can also add or remove other macro electrons to represent a full ionization event. In field ionization, we have ions emitting electrons in the field of strong lasers. In collisional ionization, we have incident electrons coming in with some cross-section of triggering a collisional ionization event. This is that cross-section as a function of incident electron energy. And there are similar rules for recombination as well. Now, it can get a bit complicated balancing all these particles of different weights. So imagine you have an electron comes in and it ionizes something, but the electron has a weight of 1 and the ion has a weight of 100. Do we really think this electron has enough strength to ionize 100 ions? That might not conserve our energy if it doesn't have enough binding energy to ionize 100 ions. We have to be quite clever with the way we do this if we have macroparticles of very different weights. So let's consider a brief example here. We have an incident macroparticle which has weight W1. That's how many real particles it represents. Each of those incident macroparticles has an interaction chance of P delta T, the thing that I said at the very beginning, based on the rate of that process, which means that we have W1 particles, each with a P chance of affecting a background. We would expect W1 times P delta T particles to be affected by that incident particle. So what we can do then is we can start pairing our incident particle to ions in the same cell, and we can just keep ionizing them until we have ionized enough that we are able to say, right, we've actually ionized enough particles now, we can just do the last one based on probability. So in this example, we have N2, we want to create 10 ionized states. We pair to the first ion, it has a weight of 4. 4 is less than 10, so let's ionize it. Now we need to do 6. The next one is also a weight of 4. 6 is greater than 4, so we'll ionize it. Now we only need to do 2 more. This is a weight of 4. Let's ionize it, but only with a 50-50 chance, so that on average, we will have ionized 2, even though it has a weight of 4. So on average, we are creating the correct number of ionizations, even though that these are different weighted particles. Oh yeah, and after we do this, we can just trigger the chance of that electron losing energy because of it being transferred to bound electrons. And this creates the right energy loss on average, and it creates the right number of ionized particles on average. And finally, let's talk a bit about collisions. So I mentioned at the start that we only have one field point per cell, which is good for the bulk motion of plasmas, but it's very bad on a particle-to-particle level, because these particles should be scattering off each other, but they're not, because there's only one field point per cell. We're not considering the relative fields of each one. We can get around this by having a sort of hand-wavy collisions package that we can stick in and model things instead. And what we do with this is we use a binary collision algorithm which estimates how much these particles should have been scattered in a given time step, and then applies that scattering. So there's a very good numerical experiment to describe this that was described by a person called Nambu. They did this numerical experiment where they have a single test particle and they fill in a load of particles for it to collide with at random distances from it, between some Bmax and some Bmin impact parameters. We're going to say that it's a large angle scatter if it's bigger than this, or if it's smaller than this, and we're going to say that it's going to be completely ignored, it'll be screened by the other charges if it's bigger than this, which creates a cylinder of particles which will contribute to cumulative small angle scatter. So let's populate particles in that cylinder and calculate the scatter from each individual one. So theta k is the scatter after k collisions. So pair two particles together, do a scatter, then that first particle will pair to another one, do a scatter, 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 and we can look at the range of angles after many, many scatter events, which is what this is. This is the cumulative scatter angles after n collisions. So when n is 100, specifically these are for small angle scatter collisions, which actually turn out to be the dominant mode of scatter, because there's so many of them. After a small number of small scatter collisions, we have a curve that looks like this. Now this is a cos chi n at the bottom, which means that most of the scatters are around here, and that corresponds to small scatters. And that makes sense physically. After a small number of small angle scatters, the total scatter is small. That's not a controversial thing to say. But as we go to higher and higher scatters, this distribution gets flatter and flatter until by the time we get to 3,000 scatter events, we have a flat curve, which for this distribution and for this x-axis here corresponds to an isotropic scatter. So after many, 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 many scatters, you can't tell what your original direction was because you have an isotropic distribution. And what Nambu did, which was very clever, was they decided that if you squint really hard, these are approximately straight lines. And so they created a fit of straight lines which sort of rotated as the number of scatters increased. And they have this sort of scatter angle sampling based on the total number of scatter events which you expect, which varies with things like relative speed between your incident particle and your background, the Coulomb logarithm, the time step that you're looking at, the number density of background particles. It all comes out to form this general scatter angle as a function of time. And, I guess I put all the examples at the end. So for that last bit, if you're interested in modelling field ionization, there's a good little test in example 3.4, where we shoot a 3 times 10 to the 15 watt per square centimetre laser at a block of neutral carbon. And we can look at how the number density of the carbon species changes over time. Starts off completely neutral, then we have carbon 2 and carbon 3 by 42 femtoseconds. We do this by setting this ionized term in our species block. So ionized is T. Ionized limit says, well, how many ionization events do we want? You don't need to set that, but there's no point in creating empty species if you don't ever expect them to be filled. So that's why you might want to do that. And if you want each carbon to emit to a different species, so electron from carbon 1, electron from carbon 2 in different species, you can set this parameter as well. Otherwise, you need to manually tell it which electron species to eject particles to. For collisions, there's a good collisional test where we do collisional equilibration. You start off with 2 overlapping particle distributions, one at 1 keV, one at 500 electron volts, and then even though they start off with very different distributions of energy, after spending a long time colliding with each other, after 300 femtoseconds in this case, we'll find that they have equilibrated and both species have the same thermal distribution from collisional scatter. There's a few different keys here. You can have a Coulomb log is auto, where it recalculates the Coulomb logarithm each step. That's very slow. We don't recommend you do this if you wanted to do that. Instead, it's better to pick a sort of typical Coulomb logarithm value to use and just plug that into your collisions package. So Coulomb log equals 5, you could say. 5 is usually good enough in a lot of cases. You have to tell it which species you want to collide together. So in this case, collide equals all. You want to do... collisions are actually very slow. So what you can do instead, you can run the collisions package once every, say, 10 steps for a time step which is 10 times longer than the simulation time step. You should get the same number of collisions total, but you do the collisions calculation a bit less often, and it makes the simulation run a lot quicker as a result. Oh, and I guess that's it. So yeah, that's all the physics packages which I would like to cover. If you need any help getting any specific physics package set up, just give us a shout. We'll be floating around now till the end, I think.
5 o'clock, yeah.
Which is at 5 o'clock, so the 40 minutes of EPOCH Workshopping.